Okay, isomorphisms. In the previous lecture, we showed that you can redraw graphs, right? And make them different. You can have different drawings of graphs. And you can ask yourselves, are these two drawings the same drawings of the same graph, right? Because a graph is really just a list of vertices and a list of edges. And you can draw them in lots of different ways. So are these two graphs isomorphic? Well, they could be. Let's throw in some labels here. We'll call this vertex A, B, C, D, E, F, G, and H. Notice that this is a bipartite graph, right? There's a pile of vertices on one side, a pile of vertices on the other side. These vertices are not connected to each other. These vertices are not connected to each other. Edges connect vertices on this side to vertices on that side. And so this version of the graph emphasizes that it's bipartite. This is the same graph, just drawn in a different way. This emphasizes that there are no crossings, right? So you can draw this graph without any crossings at all. And crossings will become important in the next lecture. So are these actually, well, they are isomorphic, but how do you show that they're isomorphic? Well, can you identify these vertices over here? So A is a vertex that has three things coming out. So it has to be either this one, it's a degree 3 vertex, so it has to be either this one, or this one, right? Because this is degree 2, this one's also degree 3, this is degree 2, this is degree 2. So A is a degree 3 vertex that's connected to one degree 2 vertex. It's connected to a degree 3 vertex and another degree 2 vertex. So this could be A, right? Because it's connected to the right things in the right way. So what are the other vertices? Well, A is connected to a degree 2 vertex, E, and E is connected to another degree 2 vertex. So this one would have to be E, right? Because it's connected to A, and the other vertex that it's connected to is degree 2. This one, we hope, would be F, right? And F is, no, this would have to be F. We hope this is G. G is connected to a degree 3 vertex. This is connected to a degree 3 vertex, so this would be G. And then A is connected to F, and this should be F. Right? And so all the assignments work so far. If this is E, then this would have to be D, and D is connected to H, and so that works out pretty well. If this is H and this is F, well, G, we know is connected to C, so that would have to be C. So is C connected to F and H? C is connected to F, yes, C is connected to H, and C is connected to G. So that actually worked out nice and consistently. And what's the other one that we have left? F is connected to A, B, and C, A, C, so this must be B. And as a final check, is H connected to C, D, and B? H is connected, in fact, to D, to C, and to B, so that works. So, right, you can tell that they're isomorphic because you can assign these letters to this and get a consistent thing there. Invariants are things that are true about a graph regardless of how you draw it. So degrees of number of vertices, this has got 8 vertices, this has got 8 vertices. Number of edges, if you count up all the edges, these two graphs have the same number of edges. Degree of the vertex, 1, 2, 3, 1, 2, 3. B has got 2, B has got 2, C's got 1, 2, 3, C's got 1, 2, 3. Remember that when you think about the definition of a graph, you've got a vertex and a list of all the edges that come out of that vertex, right? And so those have to match up. Coloring, how many colors you need to color a graph is an invariant. How many end cycles? So this has got 1, 2, 3, 4. There's a 4 cycle. We should be able to find A, F, C, G, A. Right? There's a 4 cycle there. So the cycles in one have to match up to the cycles in the others. So, having an Euler cycle, having a Hamiltonian cycle, these are all called invariants. So if you're given two graphs, two pictures, and you want to show they're not isomorphic, or even just two lists of vertices, you should try to find invariants that are different in the two graphs. So are these isomorphic or not? How do you tell? Well, this has got 1, 2, 3, 4, 5, 6, 7, 8 vertices. This has got 1, 2, 3, 4, 5 vertices. So not isomorphic. These are not the same graph. Right? They're not two different, oh, sorry about that. These are not two different pictures of the same graph. And maybe I should not be using blue. It says 8 vertices. 5 vertices. Not isomorphic. They're two different graphs because they have different properties. And there's lots of things that are different about them. This one has no cycles at all, right? This one has lots of cycles. This has degree 1 vertices, several of them. This does not. This is actually like what's called a tree, and it's very different from this kind of a graph. So you can just look at two graphs and say, well, here's a property that one has that the other one doesn't, and so they're not isomorphic. But the properties are not properties of how they're actually drawn, right? Number of crossings, for example, that's not an invariant. This one has lots of crossings. This has no crossings, right? So having crossings, the number of crossings there are isn't an invariant because it really depends on how you choose to draw the graph. Okay, are these two isomorphic? But not, because that's what the problem says, but why not? Well, start checking the basic things. Number of vertices, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So that's okay. That doesn't rule out them being vertices. Number of edges, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the one on the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 on the one on the right. So number of edges, that doesn't mean that, I mean, those match up. That means they might be isomorphic, they might not. We just don't get any information from that. Degree of vertices. One on the left has got 1, 2, 3, 4 of degree 2. And 1, 2, 3, 4 of degree 3. The one on the right has got 1, 2, 3, 4 of degree 2 and 1, 2, 3, 4 of degree 3. So that doesn't tell us anything about whether or not they're isomorphic or not. Note that neither one has an Euler cycle because they have degree 3 vertices. You could look and see if they have a Hamiltonian cycle. If you start here, you'd have to go here, around. And so maybe the one on the left doesn't have a Hamiltonian cycle, it looks like, because you'd have to, if you start here, you'd have to do this trip at some point. And then if you tried to go in, you get stuck and you can't actually do things. What about this one? You'd have to go around, and then you can go in, you can go out. This one looks like it has a Hamiltonian cycle. That would be a way to tell the difference between these two graphs. This one has a Hamiltonian cycle, and this one doesn't, because you can't actually get around there. So there's a couple of different ways to do this. Another property that you could look at is that, what was it? This is a degree 3 vertex. Oh, right. So here, your degree 2 vertices on the left, degree 2 vertices are all connected only to degree 3 vertices. So if you look at this, this is connected to 2 degree 3s, this one's connected to 2 degree 3s, this one's connected to 2 degree 3s, this one's connected to 2 degree 3s. But on this one, you've got a degree 2 vertex that's connected to another degree 2 vertex. And so that's a difference between the two graphs. And so they're not isomorphic because there's structural properties that are different that aren't just artifacts of how you chose to draw them.